All right, next problem. We got two small vehicles are placed on opposite sides of a straight track facing each other. So let's draw the track here. Track is 100 meters long. The experiment is conducted in which the cars move toward each other with constant velocities until they crash into one another. All right. The cost of fuel for the first car, let's say car A, is the square of the distance it moves, and then right. So we have a cost function. I'm going to go ahead and start creating that. It's 4 times the square of the distance it moves. So let's say 4a squared. Cost of fuel for the second car is 2 times the square of the distance it moves. 2b squared. Experiment wants to minimize the total fuel cost. Right, so we're going to add these two things. How far should the first car travel? All right, so this is your cost function. This is what I'm going to be optimizing. And then there's a constraint here, right? This is similar to the wire problem. I know that a plus b is equal to 100. All right, so in this case, if I solve for a is equal to 100 minus b, and I can plug that in. All right, so this is now your function in terms of one variable. My constraint allows me to say that a has to go from 0 to 100. But you can also argue, in this case, that you can say 0 to 100, right? You could say the car A wouldn't move, and then just let car B go straight across. Or you could say, well, let's have it all car A, and then car B will just be sitting waiting at the other end. Right? We haven't done a open interval or closed interval yet, so I'm gonna try it this way and see what happens. All right, we are minimizing cost. All right, so we've got the constraint, we've got the domain, we're ready to take the derivative. Before I do that, I'm going to FOIL this out. If I distribute this part out, I'm going to get 10,000 minus 200b plus b squared plus 2b squared. All right, then if I distribute the 4 out, 40,000, too many zeros, minus 800b plus 4b squared plus 2b squared gives me 6b squared. All right, and then I'm going to take the derivative, negative 800 plus 12b is equal to c. All right, so if I solve for b here, right, this is c prime. If I set this equal to 0, which is 200 over 3. All right, and then I can take the second derivative. Oh, sorry, I don't need to do that. All right, so since we're doing a closed interval, what I can do is I can plug. Oh, maybe I shouldn't do that. Oh, sorry. So I'm going to plug the critical points and the critical point and the endpoints. Into my function. Right, so my function is right here. right. Okay, so all right, I'm just setting up my table and then plugging my numbers in. All right, and then if I do 100, right, so this gives me my, using the EVT here, right, notice that the cost is minimized at this value. So if this is my B, it's asking for how far should the first car travel. So A would be 100 minus 200 over 3 would be my answer here. This is meters. All right, so here's an example where you can use the extreme value theorem to prove that you have a min.